Okay, hi, I'm Euijong Whang, an associate professor with tenure at the Data Intelligence Lab at KAIST EE. Today I'll talk about our recent work on data-centric responsible AI. So just to give some more introduction of myself, I obtained my PhD degree in computer science at Stanford University, and I then worked at Google Research as a research scientist for 5 years, and then I joined the KAIST faculty from 2018. Currently, I have 7 PhD students and 3 master's students, and I also have some alumni. So the 2 main research directions of our lab are data-centric AI and responsible AI, and I'll give you more details in a moment. So nowadays, as AI is used in our everyday lives, responsible AI is becoming increasingly critical. So a lot of companies like Google, Microsoft, and Samsung are all emphasizing the importance of responsible AI as follows. So in addition to just being accurate, it's also important to use AI responsibly and ethically and transparently, and so on. So the key issues are as follows. It's actually a long list. The objectives include fairness, robustness, privacy, explainability, security, value alignment, and so on. And so far, our focus has been on the top 4 objectives. So now I'd like to explain data-centric AI and first make a contrast with model-centric AI. So model-centric AI is the traditional notion of AI where the goal is to improve the training algorithm to increase model performance. In comparison, data-centric AI aims to improve the data to increase model accuracy. So there are a lot of steps involved in the data preparation step. So first, you need to acquire data and start with something. Then you need to label the data and make sure you have the answers to train on. Then you need to validate the data and check if there's anything wrong regarding the quality of the data. And if there's a problem, you need to clean the data. And if you don't have enough data, then you need to sometimes augment the data. And if you have too much data, sometimes you need to sample or filter the data as well. So all of these steps are very important for improving the model performance. So as I mentioned, our lab focuses on satisfying these 4 responsible AI objectives. And we combine these objectives with the data-centric AI objectives and solve the combinations of problems. So you can see that towards the left-hand side, you see a lot of data management topics like acquisition and labeling. And there we have solved responsible AI problems and published papers in data management venues. For example, we publish in top database conferences like Sigmod and VLDB. In the middle, we also publish in data mining venues, top venues like KDD. On the right-hand side, we also publish papers in top machine learning venues, including ICML, NeurIPS, and iClair. More recently, large language models have become increasingly important, and we also solve data-centric responsible AI problems in this domain as well. So on the bottom, you can see that we have some contributions, recent publications on benchmarking and fine-tuning. So all of these works shown on the screen are from our lab. And what's the final goal? So if you go to a sandwich place like Subway, you have the option to select all ingredients in your sandwich. So you can just say, give me everything. And that's exactly what we want to achieve. So instead of just satisfying like one objective for responsible AI at a time, our ultimate goal is to satisfy all objectives of responsible AI. And that's very challenging because these objectives are often contradicting each other. And so you need to make a lot of trade-offs to satisfy all of them. And we like to solve these problems starting from the data, right? And in all steps of machine learning. So today I'm going to briefly talk about 3 recent works from our lab. Falcon, which was published in VLDB this year, RC Mixup, which was published in KDD, and ER-Bench, which was published in NeurIPS. It will be published in this year's NeurIPS very soon. So the first work is titled Falcon, Fair Active Learning Using Multi-Armed Bandits. And this is work by my previous student, Ki-Yeon Tae, and current student, Jae-Young Park. And this is a collaboration with our friends at Georgia Tech. So we focus on the problem of fairness in machine learning, where the goal is to not discriminate. So this is part of, again, one of the objectives of responsible AI. And below, you can see some use cases, some examples of where fairness can be a critical issue. So on the bottom left, you can see the headline saying that AI bias caused 80% of black mortgage applicants to be denied. So it's actually a serious problem. If you just use AI without any thought, sometimes it may just discriminate against different races or different genders and so on. We focus on the problem of active learning, and first I'd like to give a brief introduction of the traditional notion of active learning. So here, the goal is to select samples from unlabeled data for labeling to maximize accuracy. And the goal is to minimize the data to label because labeling involves expensive human resources. So you don't want to label the entire data. Instead, you want to be selective and just pick the most informative samples to label, right? So in the figure below, you can see that we're selecting like 2 samples from the 4 in hope that it will maximize the improvement of model performance. So what is our problem? So we would like to solve active learning, but also by where we also improve fairness in addition to accuracy, right? So the goal is to also take into account improving the fairness measures. So on the bottom left, you can see that we have unlabeled data, but they can be divided into 2 sensitive groups, white and black. So these can be races, or these can be genders, or they can be any other sensitive groups. And here, we might choose to select samples in the black group so that the fairness is improved. So I'd like to be a little more concrete on this. So in the bottom example, on the left-hand side, you can see that we use the fairness measure, a very typical one, that requires an application to have a similar positive prediction rate for different sensitive groups. So comparing the black and white sensitive groups above, you can see that the positive prediction rate of the black group, denoted as p y hat equals 1, is 60%, while the positive prediction rate of the white sensitive group below is 80%. So this means that there is some unfairness here, and that can be problematic when we're, for example, hiring people. So here, what we would like to select for labeling is a black sample that has a positive label, as shown in the middle of the example. So this will in turn improve the positive prediction rate of the black sensitive group and thus reduce the gap between of the positive prediction rates and thus improve fairness. So that's our goal, but the problem is that in an active learning setup, we do not know the labels in advance. And therefore, we might end up labeling the wrong samples that have a label that we do not want. For example, a black sample that has turns out to have a negative label. The problem is that this would actually decrease the positive prediction rate of the black group and thus worsen the fairness level, right? So the positive prediction rate, 60%, would actually go down. So our solution is to propose the following technique called Falcon, where we select subgroups to label and using a trial and error method. So intuitively, we first pick a sample and then we label it, and based on the actual label, we decide to either use it immediately or postpone using it. So it's a very simple idea, but very effective. And we also identify more helpful samples from the subgroup using adversarial multi-armed bandits. So this involves a little technical details, which I'm not going to cover today. But basically, we like to adjust how aggressive we are in choosing samples that are likely to be helpful for improving fairness. And we kind of balance that of how much risk-taking we want using multi-armed bandit techniques. In addition to these 2 techniques, we also balance fairness and accuracy by alternating the fair selection with traditional active learning that focuses on improving the accuracy. So as a result, we can improve both fairness and accuracy, or actually make a good trade-off between the 2 objectives. Okay, so moving on to the next work, I'd like to introduce RC mix-up, data augmentation strategy against noisy data for regression tasks. So this is work done by my two PhD students, Sang-Hyun Whang and Min-Soo Kim. And this was presented in this year's KDD conference, a top conference in data mining. So here, the problem we tackle is that improving the, increasing the amount of data we have for training AI. So as AI models become bigger, the lack of data is becoming a more and more serious problem. And so you can see a lot of headlines like the following that talk about how the internet is too small for training nowadays. So obtaining enough training data is crucial. So data augmentation is one technique you can use to kind of compensate for this problem. So this is used to increase the amount and diversity of data without actually collecting new data. And there are many techniques for augmentation. The representative ones are image processing techniques like rotating and flipping images, or using generative models to generate brand new images or any other type of data. In this research, we focus on the problem of regression, where the goal is to predict a number instead of making some classification between like 0 and 1. And even here, the lack of sufficient training data is one of the main challenges when training models in regression. So there is a state-of-the-art technique called C-mix-up, proposed by Yao et al., that is specialized for augmenting data for regression by mixing samples with similar labels. So looking at the example below, on the top you can see there are two images of children. And let's say that the task is to predict the age of each person. Now, if you look at the labels, the two labels are pretty similar. So you see a 2-year-old and a 1-year-old. And so in this case, a C-mix-up would mix these two images and produce a mixed image that's sort of in the middle of the two that has a year of age of 1.5 years. So this mixed sample is likely to help with the regression task and the accuracy. On the other hand, if you look at the bottom example, you can see that there are two images that are very different in terms of age. So the left-hand side image is 53 years old, while the right-hand side is 1-year-old. And here, C-mix-up would not mix these two because mixing them would result in some very strange image that does not help with improving the accuracy. So this is a great work, and however, C-mix-up is not really designed to operate on noisy data, which is the focus of our research. So labels can indeed be noisy in real-world applications, such as manufacturing, where you might have a lot of measurement errors and product defects and incorrect labelings. And noisy labels may cause C-mix-up to incorrectly mix samples, leading to worse model performance. So going back to our example below, if the bottom left image of the person who used to be 50 years old is now labeled as a 1-year-old, then C-mix-up would not really take that into account and simply mix the two images and produce the weird looking image on the right-hand side. Okay. So we performed some initial experiments showing that C-mix-up is indeed vulnerable to noisy data. So we evaluate C-mix-up on noisy data, where we add label noise to a data set called Spectrum. This is a manufacturing data set. And we compare it with a typical empirical risk minimization. And as a result, regardless of the noise ratio, the RMSE, which means stands for root mean square error of C-mix-up, increases as much as ERM's RMSE, as shown in the plot below. So basically, the x-axis here is the noise ratio and the y-axis is error. The more noise we have, the higher the error for ERM and C-mix-up, which is bad. So to deal with noisy data, we consider also utilizing robust training methods. Robust training is to clean or by selecting or refurbishing data for training accurate models against noisy data. So intuitively, looking at the cartoon below, if you have blue points that are clean and red points that are noisy, we like to remove as many noisy points, the red points, as much as possible. So we combine two techniques, data augmentation and robust training, that at first glance seem to be contradictory because data augmentation is about adding data, while robust training is about cleaning data. And we integrate the two techniques tightly and formulate our problem as solving the following bi-level optimization problem below. So the problem number one is the data augmentation problem, and the second problem is the robust training problem. So the key idea is to tightly integrate these two operations for a synergistic effect. In particular, we integrate C-mixup with a technique called ITLM, proposed by Shen et al., which iteratively cleans the training data as the model trains. So the overall algorithm is shown below, where during step one, we have a cleaning phase where we choose points where the model's prediction is very different from the label, and we clean them. We remove the noisy samples as much as possible. Then, during step two, we use C-mixup to augment the data, and also we tune C-mixup as needed. So the star points there are the mixed samples, and they have two effects. One is that they augment the clean data, and they also have the interesting effect of diluting noisy data. Finally, during step three, we update the model so that we can go back to step one and improve the cleaning process. And this process iterates until convergence. So the third work I'd like to introduce today is called ER-Bench, an entity relationship-based automatically verifiable hallucination benchmark for large language models. This is work by my PhD students Jio Oh, So-yeon Kim, Junseok Seo, and this is a collaboration with our collaborators at Microsoft Research Asia. And this paper is going to be published in Europe's 2024 as a spotlight paper in the dataset and benchmarking track. So the motivation of this research is that large language models are very useful, but they also hallucinate a great deal. So hallucination occurs when LLMs generate false or non-existent information. And factual hallucination greatly undermines the reliability and trustworthiness of LLMs. So if you look at the example below, let's say that we ask the question, are Firenze and Florence the same city? On the left-hand side, the LLM answers yes, because they are of the same city in Italy. And so in this case, both the answer and the rationale are correct. But on the right-hand side, you can see that the LLM answers correctly yes, but gives the incorrect rationale, saying that they are the same city in, say, China. So for our benchmark, we like to evaluate both the answer correctness and the rationale correctness. So what are the challenges of hallucination evaluation? So there are a great deal of manually constructed benchmarks, but these tend to be precise but lack scalability. There are also many knowledge-based benchmarks that are scalable, but they mainly focus on answer verification instead of rationale verification. So they don't check whether the reasoning is correct sufficiently. Lastly, LLMs continue to evolve. So every day we see like a new LLM that's being developed, productionized. And this requires dynamic evaluation and complex questioning. So the benchmark itself has to keep on improving so that they can properly evaluate these advanced LLMs. So the key idea we use for this benchmark is to utilize relational databases. Relational databases are based on the relational data model and assume the fixed schema. And a fixed schema enables data integrity based on database design theory. And here we can use integrity constraints like functional dependencies and foreign key constraints that can be utilized to construct question-answer pairs. So let me illustrate with the example below. So in databases, it's very typical to start with an entity relationship diagram, as shown in the middle of the screen, where you have entity sets like director, movie, and stars, and they have a bunch of attributes and relationships. Now, these can be used to construct, create three tables below, director, movie, and star, that have the following attributes, as shown on the bottom left. On top of this schema, you can impose so-called integrity constraints. So for example, you can see that there are three functional dependencies on the bottom right. The first one says that for movies, if two tuples two records have the same title and year, then well, if you know the title and year, it determines the director and length of the movie. So basically, if you know the title and year, you also know the director and length. And you can see other functional dependencies as shown below. You can also impose foreign key constraints, which connect attributes in different tables. So on the bottom left, the director attribute of the movie table refers to a director. So whenever you have mentioned a director in one of the movies, it has to exist as a director record in the director table. So we can, using these integrity constraints and the database, we can perform dynamic question construction by generating question templates based on the functional dependencies and apply them on the entities. So continuing with our example, let's say we use the functional dependency, title, year to director length, to construct the following questions. First, we can create a binary question template like the one shown in the middle, asking, is there a director who directed movie title released in year? And the answer for this can be yes. And what we're going to look for in the rationale is whether the LLM correctly pinpointed the director of the movie as well. And we can also construct multiple choice questions as shown below. We can also construct multi-hop questions by joining multiple relations using the foreign key constraints. And so in the example below, we can, the first example shows how we can join the movie and director tables to create like a join table with, and also expand the functional dependency and foreign key constraints and ask more complicated questions. We can then use the functional dependency to pinpoint critical keywords that must appear in the LLM responses. And based on the database design theory, these keywords are context insensitive. So for example, let's say that we ask the question, is there a director who directed the movie Star Wars released in 1977? And the answer can be yes, and followed by a rationale saying that the director named Steven Spielberg directed the movie Star Wars. So while this looks very convincing, it's actually incorrect because the correct director of Star Wars in 1977 is George Lucas. And so here we can determine that the LLM's rationale is incorrect. So to summarize the benefits of ER-Bench, compared to manual benchmarks, ER-Bench is more scalable and dynamic. And compared to knowledge-based benchmarks, ER-Bench offers automatic rationale verification and easy multi-hop question construction. And another benefit is that using our benchmark, anyone who has a database can convert their own data set into an LLM benchmark to evaluate both the accuracy, the answer, and the rationale. So we have a lot of experiments in our paper, and here I'll just show you one example. So this shows how different LLMs show different hallucination behaviors with respect to answer and rationale. And I won't go into all the details, but here we're comparing like 6 state-of-the-art LLMs on 5 different data sets. And we use various types of questions, prompts, and we use 4 different metrics for evaluating the accuracy, the rationale, and hallucination of LLMs. And the observations are, some LLMs are very good at answering a lot of questions correctly. They're very aggressive, whereas other LLMs may be more conservative, but instead hallucinate less. And the key claim is that ER-Bench can be used to do this comprehensive evaluation of various LLMs in terms of answer and rationale performance and hallucination. So in summary, I just covered some recent work on data-centric responsible AI in the Data Intelligence Lab. And we continue to do various research in this direction, and we hope to keep on pioneering and leading this research field. Thanks very much.